electrons, such as, trying to think of one, think of one planet, the parts of idea. So the sp2 hybridized trigonal planner, trigonal planner, the bond angle is around 120 degrees. So in this case, it's going to be sp3 such ketone is at 109.5, and then linear is 180 degrees. Linear 180 degrees. sp3 should be around 109.5. So those are really some great relations. And then there would be sp3. Alright, in the following reaction, how many hydrogens do you add or lose? Again, just trying to see if you know how to read bond line structures in this one. So we have two hydrogens here, one hydrogen here, one hydrogen here, two here. So there's 1, 2, 3, 4, 5, 6 at this end. Here we've got 3 hydrogens coming off the end. So that's a total of 6 hydrogens also. So in this case, there's no hydrogens that are gained or lost. And the following reaction again, same thing, how many hydrogens do you have, yes or no, or how many hydrogens do you need? So there's 2 here, 1 here, 2 here, 2 here, 1, 1, 2. Those are hydrogens in this one. And then here we've got 1, and then 2 here, 2 here, 2 here, 2 here. So we've got 2, 4, 6, 7, 8, 9, 10. So 10 hydrogens here. Got 1, 2, 4, 6, 7, 8, 10 hydrogens here. So again, very similar shape. Alright, moving on. Number 13, which of the following structures contain an aromatic ring? Aromatic rings have conjugated pi bonds, so the one that would be possible is C, so that's the benzene ring. So aromatic ring is conjugated pi bonds. Number 14, which of the following pairs of structures are resonance structures? So again, resonance structures, you want to maintain the same connectivity and everything. You don't want to lose hydrogens or carbons or anything like that. And you want to make sure that you can move the charges around and try to maintain the charge as possible. So in one way it's possible, these are constitutional isomers. So they need to have the same exact shape for that to work. So one's not going to work. If we look at 2, yes, you can draw this to variance to get that bond structure. Yes, you could do that. Number 3, if you move this pi bond here, you can move the here or the positive charge to the other carbon. And same idea with this one. This one you would bring this up. So we have, okay, you would bring down this pair to there, and I'll kick off the bond to that carbon. Then this carbon will be missing a charge, so that carbon should have a charge, so this would not work. So in other words, the most stable one between this would be C. The one goes C. So again, the resonance structure. No breaking bond. And one more charge should be maintained possible. I believe test this exam one, for this one, it should be chapters 1 through 4. So if you're confused as to where to find these, it should be chapters 1 through 4. So which of the following is the correct resonance structure of A? Looking at A, if we want to draw a resonance structure of this, we should move this pi bond up to the junction. And when we do that, draw it out again, move this bond to here, we will get negative part of nitrogen, a positive part of carbon. So the one that has to go with that would be B. going down this way and moving that lone pair towards our carbon, because what you form is that you form a positive carbon is nitrogen and a negative carbon is carbon. Carbon would much rather have a positive charge than nitrogen having a positive charge. Again, the more electronegative atom will want to take that negative charge. Number 16, again, drawing the direct resonance structures of this compound. So let's do this. So you have nitrogen here. So we have allylic lone pair. So move this allylic lone pair down to this carbon and then kick this up to here. So then you will get value T. The other structures wouldn't work. I mean, again, we mentioned that carbon doesn't want to have really a negative charge, but in this case, we didn't really have a choice because the rest of the resonance structures didn't make any sense to be having all the time. So which of the following is the correct resonance structures of A? So resonance plays a big part. So what we're going to do is first move this pi bond to this oxygen. So what we'll get is oxygen that's negatively charged, a positive charge here. That's one of the resonance structures. Another resonance structure we have is that these lone pairs are localized, so they can go here. We can move those lone pairs to there. So what the resonance structure that matches up would be 8, because that was the first structure that we drew. Number 18, which is on the valid resonance pair. So over here, we broke the bond between the oxygen and carbon, so we can't use it. You don't want to break the bond. This is possible if we move this bond onto here, we would get a negative and positive charge there. Over here, we lost the hydrogen, but where did it go? Don't know. So we don't really want to break that bond yet. So we have B as the main one out of this group. Okay. And then I indicate whether the lone pairs are localized or delocalized. So again, delocalized lone pairs, delocalized electrons are going to be allylic to the double bond. And then localized is going to be benzylic. Remember, allylic is going to be one carbon away, so say these are lone pairs. It's going to be one carbon away from that double bond. So here's when two carbons connect to double bond, it's one carbon away. Versus benzylic, do something like that, where it's directly connected to that double bond. You can also see it if you have like, this is chlorine, again, that's benzylic versus this chlorine. Sorry, allylic versus benzylic. So again, keep in mind, it's still connected. So, in the first one, we have these lone pairs right here. So these lone pairs are allylic to those double bonds. Both of them are. So that's going to be delocalized. So we can cross out A and B. And looking at N, it's going to be directly connected to this vanilla double bond over here. So this way it's going to be localized. So it's going to be C. Number 20, how many resonance structures does a compound have, including itself? So, we're going to do one of the resonance structures. So, we have a couple ways to do this. If we move this pi bond down to this carbon-oxygen bond, we will get double bond here, double bond stays there. So now we have a positive charge with oxygen. So see how we maintain this positive charge, still positively charged here. It's not something that maintaining the charges. Positively charged, still positively charged. Okay. So what else can we do in this case? You could do this structure, but it's going to be a very minor structure. So when you draw this, what ends up happening is that you negative charge are here. So you want to move around each bond at least once. So when you move around each bond once, you move this lone pair once, and now you move this pi bond once. You want to move pi bond and delocalize lone pairs when you do resonance structure. So you move pi bond and delocalize lone pairs when you do resonance structure. Pi bond delocalize. So in this case, you would have a total of 3 resonance structures, but this would be very unstable, or be the most minor one, because you have a negatively charged because you have negatively charged oxygen or carbon, and you have a neutralish charge. So the charges cancel each other out. Number 21, how many double bonds the most stable contributor to resonance in question, or this is question 20. So the most stable contributor of this resonance structure would be this third one. So then we would have 2 double bonds. Number 22, in the following reaction, identify the acid and base, so the conjugate acid and base. So if we use Bronsted-Lowry definition, a Bronsted acid donates a proton. Bronsted base accepts a proton. And for Lewis acid, we're going to accept an electron, and for Lewis base, we're going to donate an electron. So Lewis deals with electrons, and Bronsted deals with protons. I believe in the book it says something about Lewis could be a Bronsted, or Bronsted can't be Lewis, or something like that. I would check. There's a little thing that he mentions in the book about both of these acids. So here we have water, so that means this oxygen grabs the hydrogen. So if that's the case, this is the base, because it's going to accept a proton, and this is going to donate a proton, so we are acid, and then that means our conjugate base and our conjugate acid. So this would be B. And even if you use the Lewis definition, over here it donated a proton or electron to kind of stabilize the hydrogen, and this oxygen gained electrons, so it still fall under the Lewis acid and base theory. What is wrong with the following arrows? The arrows shouldn't start on a hydrogen number. Arrows should always start from electrons and move to whatever. So in this case, the correct arrow sequence should be that. So you move from electron to do an electron to everything. So you can't just do that. So in other words, that will fall under C. It should start an N on the nitrogen and end the hydrogen, and the bond to the carbon should be going down to the hydrogen, or to the carbon. So, which style of acid and base reaction favorite? So this is one of the most annoying subjects that oral students hate. It's the Auriol rule of acid and base. So Auriol, remember, is atom, resonance, induction, and orbitals. You want to go in order using these four rules, other than the few exceptions that Klein mentioned. You're going to use this to compare the bases. So you want to compare your bases. Compare bases. You have to identify your acid and bases in your equation. Compare the bases. And with the Adams rule, if it's on the same row, you're going to base it off of electronegativity. So when there's an increase in electronegativity, that means it's going to be more stable, which means that it's going to be more acidic. The acid that's formed is more acidic. If it's on the same column, that means we're going down the column. As you increase in size on the column, you're going to increase in stability, which increases in acidity. Again, if you increase in acidity, you decrease in how basic it can be. So it's opposite sides of each other. So same thing with resonance. If you have an increase in resonance structure, you have an increase in stability, and the rest of the trend follows. With inductive forces, you have two types of inductive forces. You have halide inductive forces, and that's going to increase the stability. Another inductive force that you have is carbon inductive forces. If you have carbon inductive forces, you're going to decrease the stability, which means that it's going to be less acidic and more basic. For orbitals, if you have an increase in S characteristics, it's going to increase the stability. So what does that mean by S characteristics? That means SP is going to be more stable than SP2, which is more stable than SP3. And why is that? Because you look at this 1-to-1 ratio, so 50-50 for S and P characteristics. So it's 50% S characteristics. Here, if you do 2 plus 1, you get 1/3. You get 1s out of 2p orbitals, so 1/3. And you need 33% S characteristics. Here, 3 plus 1 is 4, right? So you get 1/4 out of the whole entire thing. 1/4 is the S, so that is 25% S characteristics. So that's where they get the S characteristics from, is kind of like that fraction. So let's identify acid and bases in this equation. This is going to be our base. It's going to accept the proton to become water. It's going to donate a proton, so that's our acid. It's going to be our base, our conjugate base, our conjugate acid. So we compare two acids, two bases, so this base and this base. Alright? So the negative charge is both on oxygen, so we can't use the Adams rule. So we move on to the next for resonance. Does that even have resonance stability? This does have a resonance stability. So since it has a resonance stability, it's going to be more stable and more, this acid that's formed is going to be more acidic than this acid. Does that make sense? So in other words, equilibrium will go to the side that's more stable, which is that side. So it's going to go towards the right. So equilibrium will go towards the most stable side. So more stable side. Again, I need stability because it makes more sense because equilibrium is the more stable side. I know the book uses like weak acid and weak base stuff, but I mean, this is a weaker acid, so it still goes to the weaker acid side. I just find it hard to really use that sometimes. So I need stability. Okay. 25. So for the following acid and base reactions, so this is the whole question. The acid-base reaction, this is kind of how the arrow formations work. So here we've got oxygen with 3 lone pairs, right? So it's going to extract the most stable hydrogen. The most stable hydrogen is going to be the one, again, that if we want to conjugate base, it's going to be the most stable one. So in this case, you have the choices of, well, this arrow mechanism is wrong. Because if you look at this hydrogen right here, this bond between the hydrogen and carbon is going towards the hydrogen, which isn't right. And same thing with this one. So you're stuck between either this one or this one. So the most stable one should be C, because you have 2 ways that you can build the resonance structure. One way through this and one way through that. Over here, you only have one resonance structure way, just through that. Yeah, the most stable contributor for going to R rule, so let's say you extract this, looking at the conjugate base, which one would be the more stable, like conjugate base to form, using the R rule. Using outer was going to be more stable. This is chapter 4, so acid base for chapter 4. So you need a refresh on acid base in chapter 4. Okay. 26. So which side will the following acid and base reaction favor? So again, using our rules, identify your acid and bases, and then use our rules to choose your base. And this will also be your base, your conjugate base, whichever is your acid, your acid. Looking at your two bases. If you were to make them negatively charged, so we can make this oxygen negatively charged by doing this. You would have this negatively charged oxygen, or if you take away the hydrogen, you can make this hydroxide ion, right? So they're both on oxygen, but this one has a resonance structure which would come down and form a resonance structure to this one, whereas this one would have to extract the proton to make it better. So we're going towards the left, because this would be more stable than this one, to the left. Identify the Lewis base. So I mentioned again that the Lewis base will donate an electron. So it's something that's going to donate an electron. So in this case, it will be the chlorine molecule. So we have chlorine, right? So what's going to happen is that we're going to donate these electrons to this chlorine, but then this iron will attack. So the chlorine will attack iron. That's how we call it FeCl3. So identify the Lewis base in the following reaction. So again, the Lewis base donates electrons. I was looking at that down. Okay. So donates the electrons. So here we have to mention the attached position, which means that this pi bond is going to attack this nitrogen. So this will mean that the pi bond are going to donate the electron donation. And we lose that electron in the other part. And here we got the best descriptor for this following compound. So, I wrote them that Bronsted acid or the base, Bronsted acid or base could be a Lewis acid or a base. So if it's a Bronsted, then it'll be a Lewis for sure. So let's first identify if it's a Bronsted acid or a base. So if it's a Bronsted acid, we said that Bronsted acid accepts protons. Bronsted base will donate protons. Alright? So we recommend that the Bronsted acid, Bronsted base, it will also be a Lewis acid or a Lewis base. So here we've got the electron is going to want to accept a proton to make it better. So we know that it's going to accept a proton. It's going to want to be let me just draw an equation now. Let's draw an equation now for this. So we have O negative plus, let's say we have water. Then we do this form. It's going to accept a proton. It's going to accept a proton. So then we get OH plus OH. So it helps draw an equation like that. That's the best way to do it. Draw an equation, put an acid down or something. It's going to accept the proton to make it better. So it accepts the proton. It's going to be a Bronsted acid. It's not going to be a Bronsted or Lewis acid, which is not one of the choices. Maybe I'm doing something wrong. Maybe I'm doing something wrong. Oh, acid building. Oh, I'm sorry. Acid building. We have to get to the. Right. Thank you. Yes, Catherine, if I do something wrong. So in this case, good. Bronsted base. If the differential basically Lewis goes to E. Okay. So what is coordinate the following compound? So when you're asking if something coordinate, if something decoordinate, is it going towards the is equilibrium going to go towards the product? So if we use water as an example, when we do the acid base reaction for this, we're going to get OH plus hydroxide. So now let's look at our bases. We know that this is going to be our base. This is also going to be our conjugate base right here. So comparing our bases in our real rules, this is going to be the more stable one. They're both on oxygen, so we can't use the atom group. R is the resonance group. This has resonance, so it's going to go towards the left. So is equilibrium going to this coordinated product? Is it going to the product side? No, it's not. So water cannot be used in this case. It needs to be stronger than water. So when you ask me if it's coordinated or decoordinate, is it going towards the product side? If it's not going towards the product side, then it's not going to be strong enough either. So now we have our UPAC meeting. Again, I'm not going to go through the entire rule in detail. I think at this point, in the chapter 14, you should know how to name them using our UPAC rule. So one, again, parent chain, is kind of a quick summary. Two, constituents. Three, lowest locate number. Lowest locate number. And then four, alphabetical order. Alphabetical order. And then the iso counts for naming, otherwise the other stuff doesn't count, like the di, tris, whatever, church does not count, only iso counts alphabetical order. Okay, so let's look at what we have. Our longest chain is going to be 1, 2, 3, 4, 5, 6, 7, 8. Again, if you counted all of them, I did it for you, so there's 8 going towards that direction. And so you have 2 methyl groups, that's dimethyl. This is the way I do my naming. I write down what I have. It's going to be 3, 6 dimethylls, so I know where I get everything from. And then we have this ethyl group, we'll put on the 4th carbon, 4th methyl. So E comes before M. Again, you're using the E, comparing it to the methyl of the M. So E comes before M, so we need 4 ethyl, 3, 6 dimethyl. Again, 8 is going to be octane. So you should know how to name by now with the groups. A UPAC meeting again for number 32. So cyclic chains are different from linear chains. So in this case, it's a cyclic chain, which is hexane. Cyclohexane is your parent chain. And then you have a methyl group and an ethyl group. Again, ethyl comes before methyl, so ethyl wants to have the lowest number. So it will be 1 ethyl, 2 methyl, cyclohexane, which is 8. Number 33, what is the common name of the following constituents? Here we've got 1, 2, 3, 4 carbons coming off of the parent chain. 4 carbons that has the butyl group. So this carbon is attached to 2 other carbons, so it's secondary butyl group, so it's second butyl. That's why they get the name second butyl. So isopropyl is going to be, here we have the parent chain, and it has 3 carbons coming off of it. There's a spherical hand with it. So many hands. Tert-butyl, we have, it's going to be 4 carbons coming off of it. 1, 2, 3, 4. So 1, 2, 3, 4 coming off of the parent chain. This has 1, 2, 3 carbons attached to it. So it's tertiary butyl group. That's where we get tert-butyl from. Tertiary butyl. And isobutyl looks very similar to isopropyl, but we have a carbon coming off of it and giving us a extended bond. what is our UPAC name again? Find your parent chain, all that good stuff. So we have 1, 2, 3, 4, 5, 6, 7. So 7 that's in heptane. We've got 2 ethyl groups, so that's going to be 3,5-diethyl. And then we have a methyl group located on the second carbon. So when we do this, ethyl comes before methyl. So we need 3,5-diethyl, 2-methyl heptane, which is going to be C. Okay. 35. How many constitutional isomers of C6H14 have? When you're asked to do this, there is no easy way other than drawing out all the constitutional isomers of C6H14. So if you look at the formula, you know that it has to be an alkane, because alkane formula is always going to be CH2N plus 2. So it's going to be the number of carbons times 2 plus 2. So in this case, that falls under that category. So we draw all our alkanes. We have, let's see, linear chain. I start with my linear chain first. 1, 2, 3, 4, 5, 6. So that's going to be, let's see, 3, 4, 5, 6. Okay. So that's going to be one of them. And then what I do for the other constitutional isomers is that I just cut off a carbon chain and move it around. So I have 1, 2, 3, 4, 5 now. I took one of the carbon chains and moved it here. So that's the second isomer. Another one would be, still having 5 because I can move this carbon onto there. That's still another constitutional isomer. If I do 5 again and move that bond to here, that wouldn't work because that would be the same exact thing as 2. So this and this are the same exact thing. These are the same exact thing. Okay, you can check by naming them. If they're the same name, then that's their same. So I'm done with the 5 carbon chain. Sorry, it's like going all over the paper. I realize I made more into this. So I'll start with 4 carbon chain now. 1, 2, 3, 4. 1, 2. That'll give me another carbon chain, another isomer. And then if I can't do anything more with 4, so let's go to 5. Go to our 3 carbon chain. 1, 2, 3, 4, 5, 6, 3, 4, 5. Can't do it with 3 carbons, so 3 carbon doesn't work. But with 4, let's see. 1, 2, 3, 4, it should have. Oh, there we go. 1, 2, 3, 4, 5, 6. That's the difference is that. So again, always check through all your 4s and all your 5s where you are. I just see that it's in the 4. In this case here. There should be 5 constitutional isomers. C6H14. 36, so we should have followed compounds or constitutional isomers again. Count all the carbon numbers, hydrogen, see which one matches up. In this case, 2 and 3 will match up, so it's going to be easy. I used to count them for my other previous reviews, but it's way too long to have to count for all of them. Alright. So now we have linear projection, something that everyone really hates. So linear projection. Looking down this bond, draw your eyes, looking down towards that bond. So the main stick on this front carbon, the one that's not either a solid dash or solid wedge, one of those, is this main line that's coming down. So your front carbon is going to have the stick pointing down. It's going to point down, your other 2 arms are going to come towards that direction. So what I tell you that if you're looking at it, you have a hard time visualizing it. If you're looking at it from right to left, so here you're looking at it from off the right side to the left side, then the solid line is going to be on this, it's going to be on the left-hand side. So your solid wedge is going to be on the left-hand side, and your dash wedge is going to be on the right-hand side. That's your front carbon. Looking at your back carbon, it's going to be drawn in a different color, which is a combined one, but it's drawn in a different color. On this back carbon, the main like solid stick will be pointing up. That's where my stick right here is going to be pointing up. And then we're going from right to left. So the dash wedge is going to be on the left-hand side, and then the hydrogen on the other side. So combine your 2 structures together, you will get this going here. So this would be anti. drawing your eyeball, you're looking at the compound again from right to left. So you're looking towards that direction, from right to left. So still from right to left. So again, your veins are going to be pointing up in this case, right there. Or that's your SL group, you can name SL and draw it out like that. And then there's going to be solid lines. So there's a solid line, there's going to be left-hand side of the CH3 group, and this is your hydrogen that's standing there. Okay? And looking at our back cards, now how do we like to do that with draw? I'm just going to draw it in color. So what's pointing down here is another SL group. And it's going to be a dash, and that's going to be on the right-hand side. That's on this side, and our right hand on this side. The one that matches up with that structure should be E. And we project our chapter 4. Oh, chapter 3. Alright, 39. Which of all is the most stable conformer of this chip confirmation of cyclohexane? One for diethyl cyclohexane. So again, if it's in trans position, it's going to be more stable than it's really bulky. If it's bulky, you want to avoid a transition for that bulky item. But this isn't really too bulky, so we're going to go with these, like, not trans, but like, what is equatorial transition. So this would be the more equatorial. More equatorial. Should be the most stable. If they are not. Alright, so here looking at 40, so this counts all your equatorial active positions. Here we have 1, 2, 3 active positions. There are 3 active positions here. Then we have this equatorial, I know it's hard to know, it's equatorial position. You have 1 equatorial and these 2 are pointing down axially, so 2 axial. Here is equatorial, 3 equatorial. We know this is kind of having some circumstances with that one, it's 3 equatorial positions. And then for this one, there's 1 axial, and these 2 equatorial positions. So you put them in most stable to least stable. The most stable has the most equatorial positions, so 3, 4, 2, 1. I'm going to go probably halfway through midterm 2. I'm going to give you guys a break halfway through this. So we can do this a couple fewer minutes. Well, 5 minutes time. Yeah. So how many chiral centers do these 2 compounds have in total? Remember, so chiral compounds have chirality. We're dealing with chirality. Chiral centers must be sp3 hybrid. That's the first factor. It has to be sp3 hybrid, which means that it has to be 4 bonds attached to it. Which means 4 bonds. Alright? 4 bonds. That means no lone pairs, 4 complete bonds. And it has to be 4 different groups from each other. Okay? So it's the main thing. 4 bonds, 4 different groups, no lone pairs, because the sp3 hybrid specifically has 4 bonds attached to it. So, looking at the first one right here, your only chiral centers are this one, 1, 2, and 3, right there. So there's 3 in that one. Okay? This one, there is 1, 2, 3, 4, 5. All of these are different chiral centers. There's 5 in that one, so you have a total of 8 chiral centers to both of these molecules. So, are the following molecules cis, trans, or neither? So, again, cis, when you do cis and trans, you need to be able to compare 2 of the same groups. Comparison between 2 of the same groups. Comparison between 2 of the same groups. They can be the same groups. If they're on the same side, then it's going to be cis. If they're on the opposite side, it's trans. pointing this direction, hydrogen this direction. Okay? So they're pointing in different directions, one's top, one's bottom, they'll be trimmed. Okay? Looking at this one, if you have two fluorophores, but they're on the same carbon, you can't tell they're on the same carbon, they have to be on next to adjacent carbon, so I guess that's another criteria. They should be I guess you can call it adjacent carbons, next to each other, the adjacent carbons. So, in this case, both of the fluorophores are on the same carbon, you can't tell, it's going to be neither. So this will be trans and neither. Again, don't confuse this in trans with E or Z. We'll probably have one of those later on. A lot of students do that, and that's something you should not do. Relationships. So a lot of people they can tell, like some people they can tell right off the bat what it is. I have a hard time. I have to write out all the chirality centers for this. So to do the chirality for this, we have 1, 2, 3 hydrogen on the back line. So this is going to be in an R direction. This will be R. Okay, we've got 1, 2, 3. It looks like it's going in S direction, but since your fourth group isn't on the back line, you have to flip it. When you flip it, this ends up being R. So we have R to R. They're the same chiral center. They're the same exact molecule. So they're the same, which is B. So yeah, if they're an enantiomers, all the chiral centers, and I say all chiral centers, and there's like 20 of them, all 20 of them have to flip. So it's R to S and R to and vice versa. So all of them have to flip, no matter how many carbons you have. Diastereomers, or however you pronounce it, if at least one of the chiral centers is the same. It is a diastereomer. So let's say that we have something like R, R, S, and then it flips to S, R, R. So if you notice that, yes, these two flip, but the middle one remains the same. So even though only one of them stays the same, this is a diastereomer. If this was an enantiomer, R, R, S, and then you have to flip it to S, S, R. So that would be the enantiomer. So everything has to flip for enantiomer, diastereomer, at least one of them stays the same. But in this case, these alcohol groups are both identical. They have the same chiral group. Number 4, again, IUPAC naming, know the rules already, so it's R2 pentanone. So this is a cycle chain, so there's no point in putting that one down. This has another group coming off of it, so there's no point in that one. So if you do the chirality for this, let's just start with this one, since it's on the solid line. 1, 2, 3. In that case, this would be going in the S direction, so that wouldn't work, then C is our answer. Because if you flip the chirality for C, it should be R. Number 5, again, it's another IUPAC naming. Again, similar thing, we're just having to deal with chirality centers. So, if we do the numbering for this, it should be 1, 2, 3, 4, 5, 6. Then we do the chirality center. Make sure the chirality center first. So this group, that group, hydrogen coming off of it. So when you have the same atom attached to these tying off of it. So they're all carbon. So this carbon right here is attached to a carbon, carbon, hydrogen. That is what hydrogen will see on that. Right. This carbon here is attached to a different color. This carbon here, if you're ignoring the chiral center, is attached to a carbon right here and the two hydrogens coming off of it. Okay? Looking at the other one right here, this carbon right here. This carbon right here is attached to this carbon and the two hydrogens that are stuck on it right there. So carbon, carbon, hydrogen. So this one beats the other two, so this would have the first priority. So this is priority number 1. I'm sorry, draw it real quick. Now looking at this carbon right here, for this carbon, it's going to be attached to 3 hydrogens coming off of that group. Looking at this carbon right here on the other side, it's attached to that carbon coming down the bond, and then 2 hydrogens coming off. So in this case, this carbon wins because it has a higher priority. So it will be 2, 3, and then this little hydrogen right here. It's 4. So I just rewrite it out here to make it look a little nicer so I can see it all. So 1, 2, 3, 4. The 4th group is not on the back line, and the 4th group always has to be on the dash line. So when you flip this, the 1 and the 2 flips, 3 and the 4 flips. This is now going in R direction. So it's going to be R something. So R, we have those hexane as our parent chain. We have an ethyl group and an ethyl group. So this should be B. So this one ranks the highest from highest to lowest priority. What the professor meant when he made this test is that he's ranking them from naming. So naming wise, how would you do the ranking for naming wise? Naming wise. Yeah, it was really by naming. So by naming. So he said it was going to be D. So we do the naming wise. You guys remember the ketone groups come first for naming, then alcohol, then amine groups. Double bond ones are a little funky to kind of go with, but usually I'll leave the double, I'll say it later. And then we have alkane. So double bond and triple bond, what I mean by that, when you're naming them, this is kind of, those of you that take the ACS or about to go into Orgo 2, or some of you might see that at Professor Gerasimelda. If the priorities are tied, so let's say we have a double bond here, triple bond here. That should be labeled this way. So this double bond can be either named 1, 2, 3, 4, 5, right? So in this case, your parent chain should be Y and your parent chain is the triple bond. But let's say that they are tied, triple bond, double bond there. So they can either both be named 1, 2, or the double bond can be named 1, 2. When they're tied with priority, the double bond has a higher precedence, so that the parent chain would then be E and E. And then your triple bond would be the lesser one. So again, if you're tied with priorities, the double bond has a higher priority over the triple bond. And if you have they're not tied. And that's something for like more so the ACS or Dr. Bio or something like that. Not sure. Unless I leave it for Dr. So identifying the relationship between the two structures. So we have to do the chirality for each of these. So if you do the chirality for it, it should be R, R, S, and it's going to go to S, S, R. Okay. So notice how this S is this S right here, because it's OCH3, OHC group is also said as OHC group. So they're the same, they kind of like try to flip this, try to confuse you. So this center is same as this center. This center is same as this center. And then this center is the same as this center. So if you draw this out, so we have R, S. You're going to invert it to green is now R, blue is now S, and red is now S. So we look at this, R to R, R to S, S to S. So this stays the same, this changed, but then this one stays the same. So you have two of the centers staying the same. So that means they are diastereomers. Remember, one of them is the same, are diastereomers. So be careful with that, don't assume that they're already over. So number 8, drawing or schema diagram of butane. So you draw a diagram of butane out. This bromine should be on the dashed line, and this bromine should be on the solid line. And you draw the other direction of the flip. So if you do this, the chirality centers for each of this, they're symmetrical. This one's going to be S, this one's going to be R. So if they're symmetrical and the chirality centers invert on top of each other, they're going to be called a meso compound. So in that case, the meso compounds need to have a plane of symmetry and the chirality centers have to converge upon each other. In this case, they use the S one. Number 9, so S negative series, this is just more like a concept question. If it's negatively, if it's a negative right here, that means it's going to be rotating in a counterclockwise area. So it's just a concept question of whether you know whether negative or positive is counterclockwise or clockwise. Alright, so assigning R as configurations to each of these areas. So if you do configuration, there's going to be S, this is going to be R for this one. So S and R, which is D. Again, I'm not going to bother going through it. If you need help going through it, come up and ask afterwards, or raise your hand. Otherwise, you should do it. Number 11, how many meso compounds are there in the following structure? So this has a plane of symmetry. So this has a plane of symmetry. This doesn't have a plane of symmetry, so that doesn't work. And this one has a plane of symmetry. Okay, so those all three have plane of symmetry. So this make sure the characters converge. So we go from R to S in this case. So that one inverts. This one is going from R to R. That doesn't invert. This is going from S to R. So the only ones that are inverting upon itself are A and D, which is 2 structure. 2 meso. Number 12, again, this is another concept question after I asked the professor about this when I first did it for him. He said it's going to be B because if you put a cyclic compound in a polymer, it's hard to isolate that cyclic compound. So ideally, choose between the two, the acyclic one would be better to be verified to isolate in a polymer. And we have Fisher projections. So Fisher projections, we should know, so it looks something like this. And the way it's supposed to is that it looks like a dead fish almost because you have the solid wedges are go up and down, right? And you have your fins coming out like that. So you got like a fish head, you got it. So the dashed lines are up and down. That's where your dashes are, and the fins are like the solid lines. So that's a good way to learn Fisher projection. You don't know which way you dash your solids. So looking at Fisher projections, the way you should rotate Fisher projections is, okay, here we have priorities of 1, 2, 3, and 4 for priority, right? So I redraw my priorities out. You can automatically rotate it and flip it, whatever. It's going in R direction right now, so the right direction should be an S. This should be an S. But I'll show you how that you can rotate it. When you rotate it, you want the 4 group to be on the dash line, right? You don't priority has to be on the dash line. So you want to do like an umbrella. Hold down one part of it, like that one, so leave that one alone. And it's going to rotate that 4 to the dash line. The 4 goes where the 3 is at. The 3 goes where the 1 is at. And the 1 goes where the 4 is at. So it's kind of like an umbrella. You hold it in one area and you kind of split it the area around. So now it's going in the right direction, which is the S direction. So it matches up. Either way, you can just rotate it, whatever you want to do, flip it. I show students how to do this so they have that, like that, they know how to do it. So it should be S, S. I'm not going to walk through all of them. R, R. So it should be S, S, R, R. And when you do the chirality for all of these, when you do the chirality for them, you should get B as your answer. I'm not going to go through it again because it takes a long time to go through every single one of these chirality centers. But if you do it, you should get B. If you hold down one and three, it doesn't matter when you hold down. You should do the same exact thing. Rotate the 4 to where the 1 is at, rotate the 1 to where the 2 is at, and 2 goes where the 4 is at. So this is going in a S direction. And you can split this, go in a R direction, flip it to an S. Again, it's showing you how to do it. Okay. What type of cleavage does this involve? So here we're cleaving and forming two radicals. So we're forming radicals. Your forming radicals can be heterolytic cleavage, or sorry, homolytic cleavage. So you're kind of sharing it. So it's going to be a homolytic cleavage if you're having radicals. Okay, so you form radicals. And cancel that. Heterolytic, you're going to form ions. So you're going to break apart bonds with positive and negative charge something. So in this case, we have a homolytic cleavage followed by a heterolytic cleavage. So that is going to be C. All right. Why is entropy negative for ring closures? Again, this is a complex question from the book. It's just because closing a ring restricts the rotation around the carbon-carbon bond. So it's linear carbon-carbon bonds, you know that the sigma bonds can freely rotate it, but then if you put it in a ring, they're not able to rotate. They form different shared conformations and gold conformations. Number 17, which one would you say has the most negative delta S? That would be D. You're going from a very, very long living chain to a even to a split compound. So this is like the biggest one. Essentially, that's why D is the biggest one. And in 18, if you have, these are gives free energy, get free energy, delta H minus D, delta S. If you have a positive delta S and a positive H, then your delta G cannot be determined because you need to look at the temperature. Is it going to be in high temperature or low temperature? Because if it's in high temperature, then it's going to have a very, very negative number for delta G. If it's low temperature, you're going to have a very positive number for delta G. So it really depends on the temperature of that reaction for it to work. And number 19 says keep on the energy diagram for a 3-step reaction. So this is going to be 1, 2 step, 1, 2, 3 step, 1 step, 2 steps. This is how many months it has for reaction. And then one more before we go on the break. What is a transition state? An intermediate state, we'll do both of these since they kind of follow each other. Transition state, intermediate state. Here, trying to draw like something like that. So we have a little energy diagram. These peaks are the transition states, and these low points are the intermediate states. So the transition state, you can't really isolate or see anything there. So in this case, it's the local maximum. And then an intermediate is where it has the two rectangles, so where it's the local minimum, and also where you can kind of see the the stuff happening there. Alright, that's it for now. Take like a 3-4 minute break. We'll do a 3-minute and then come back around 1:44, 1:43, and we'll continue off with the stuff. Yeah, of course. If you guys want to take pictures of this, feel free to take pictures. They should be in order of the stuff that we have. 4 minutes. Alright, you guys, let's start to reconvene. If you guys are taking pictures, feel free to take pictures now, but you can guys take it at the end also. So, someone asked me really quick, just look at this, go back to this real quick. Let's say that you have to draw from a linear to a Fisher projection. So, how would you do that? It's really, I do it through GSA. I actually find all the chirality, like, you see, find all the chirality sensors. So now we know that there's 4 chiral sensors. So draw your structure. 1, 2, 3, 1, 2, 3, 4. So you have 4 chiral sensors, right? Let's say that we're using this one as our blue one, So that's going in our direction. So it's a trial and error type of thing. So I'm just going to try to put the OH on this side and see what happens. Okay? The hydrogen on this side and see what happens. So when I do this, I get that 1, 2, 3, 4, and this is the rest of the chain. There's oxygen stuff attached to it. But I know it's 1, 2, 3, 4, right? If I were to flip this, it's going to be in a 1, 2, 3, so in, and that's the so we put it's going to be R. So it's going to be R, which is not what I want here. I want it to be, I do want it to be R. Okay, so that works. That works out as R. And then when I look at this one, making this a blue, right here, or it's a purple. Again, you can chirality for it. Let's put the OH on the side and see what happens. This would be 1, then the next one will be 2, 3, 4. So if I flip this, this is going to be, this is an R direction. If I flip this, it's going to be S direction. It's going S, which is not what I want for that sensor. I want it to be R, right? So in that case, when I have to redraw this one stays the same. And in this case, I just flip it on the other side, and that's the right direction. And so you just keep doing that until you flip it to the right direction. So if it's not this way, then it's the other way. Okay. All right. What am I on? Number 22. So this is again exam 2, number 22. Identifying the nucleophilic atom and the electrophilic atom. So again, nucleophiles want to have that negative charge. They want to have that negative charge to attack the center. They want to attack the electron. So some people they say like love attacking the nucleus, so they call it nucleophilic, love attacking the nucleus. So, excuse me, so when you do this, so we have lone pairs here, we have lone pairs here. So that means these lone pairs are able to attack, or they have that kind of like a negative charge to want to attack. So the oxygen is possible. The nitrogen is also possible to attack something like hydrogen or something like that. So that those electrons make it kind of negatively charged, it doesn't have a negative charge. So it's going to be both oxygen and nitrogen. So the carbon is not going to be able to do anything because the carbon, it's more negative than the hydrogen, but it's not going to really want to attack anything. So it doesn't have that whole pair for anything to attack it. Okay? But it can have a negative charge. Doesn't necessarily. Alright, so which is the proton cannot be an electrophile. Again, electrophiles have to be a positive charge. They want to be attacked. In this case, broken. I mean, it's kind of made it obvious. In this one, the electrophile in this B one is going to be the carbon, and then the nucleophile is going to be the broken. But we still have electrophile in there. Okay. Number 24, which the pattern is along, so it's attacking this carbon, and that's the pi bond to the oxygen. So it's attacking something. So we nucleophilic attack. It's going to attack that center carbon. And this is just identifying when hydrogen or proton transfer also leads to the nucleophilic attack, things like that. So here we have a rearrangement again. Remember when we go for carbocation stability, tertiary, the most stable, followed by secondary, followed by primary, and then the methyl position. Same thing with radical stability, so carbocation and radical stability are the same. So in this case, you go from a secondary carbon to tertiary carbocation, a rearrangement reaction. Okay. Number 20 stated, what is wrong with the following reaction? So what's wrong with it? This is the lead coming off. That's fine. But now we have this carbon attacking this bromine. That's not okay. So again, remember when we do electric arrows, it goes from an electron to other stuff. So in this case, the bromine should be the one attacking the it should be attacking the carbon. So it should be the other way around. So in this case, that will be arrow. Okay. Identifying the sequence of steps in the following reaction. So what is happening here? We have a proton transfer. It's taking up a proton. Alright? Then we have this, it's kind of like it looks like a nucleophilic attack. Oh no. Because we have something, let's say we have something like a halide abstracting this proton. This is going to abstract a proton, that's going to kick off the bomb together, kind of like cause a cascade effect. So initially the proton transfer is going to show the other group attacking that. So it should be two proton transfers. So it's like a cascade effect. It is going to show that something attacking the hydrogen. Okay. Number 28, identify the sequence of steps in the following reaction. So what's happening here? We have a proton transfer here. Then we have a nucleophilic attack, and this is attacking a carbon. This is another proton transfer, again, you have something, the nucleophile striking the proton, that does like a cascade effect, kind of. So in this case, it'd be B. So here, if we do this, the parent chain is going to be this thing right here. 1, 2, 3, 4, 5, 6, 7. Heptane is our parent chain. We have 1, 2, 3. That's rotating in a R direction, but you have to flip it because it's not on the fourth is on the back line. So it should be S. So it's 2S followed by the rest of the compound, which is this right here. So that's for 1, 4, 5 diamonds. So you're only looking at what carbons are attached to. So looking at this, attached to one carbon, so that's the primary. This is attached to one carbon, that's the primary. This is also a primary carbon right here. It's attached to 3 forms. Again, when you're counting primary, tertiary stuff, you're looking at how many carbons are attached. There's only one carbon attached to that carbon, so it's only a primary carbon. So in this case, there should be a total of 3 primary carbons. 1, 2, 3. Only look at carbon. Okay. 31, which of the following is a reasonable definition of a concerted reaction? So if it's a concerted reaction, it's going to happen all at once. So that would be C. which is going to be an SN2 reaction, right? Which of the following is not a possible step in a substitution reaction? Not a possible step. So here we have attacking of the nucleophile and also leaving group. That's fine. So that can happen in a substitution reaction. We can have a proton transfer substitution reaction. We could have a loss of the leaving group in a reaction, but we can't have an addition reaction in a substitution reaction. So this is not possible. So it's not. B, it's not a possible step in a substitution reaction. Substituting the compound. Proton transfer, loss of the leaving group, and nucleophilic. Number 33, which of the following is a product of the SN2 reaction. So, SN2 reaction, what's going to happen is that this is going to attack at this position, right? When we do that, we're going to have to invert the center, right? So when we do this, we get how many carbons? 1, 2, 3, 4. So 1, 2, 3. So this is possible. This is 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. It's not 5. So it should be like 4 carbon chain. But which one of these is going to be? So we look at this bromine since we changed the inversion of it. I know it looks like it should be the dash one, but actually it's B. Because we do the chirality for it. I mean, this is one of those special cases where your main unit, which was originally 1, comes off, and a new 1 comes in, and now you're replaces that 1, so it still inverts it, it's just a different way of inverting. I don't know, like for organ ones, if your person was going through something as in-depth as that, but for ACS students, our plan is to be aware of something like that. Okay. Same idea with this one, we're going to form an equilibrium. It's going to attack here, take off your chlorine group, right? So now you're substituting either B, C, or D, right? Tough choice, but again, a whole entire primary group leaving off and a new primary group coming in to replace it and inverting it will make it into B. And since it's going to be SN2 reaction, you don't want to have an answer, so you can't have B and C. Okay. 35. So the substrates for least react for most least reactive in an SN2 reaction. So a substrate is your carbocation, like whether it's primary, tertiary, secondary, all that stuff. So for SN2 reaction, the most stable one is going to be a methyl, followed by primary, secondary, tertiary substrate. Those are your most stable for an SN2 reaction. So in this case, it would be A, followed by C, A, C, and then B, and then D. D is a phenolic. Again, phenolic is very unstable, so it's going to be like towards N. So let's see, we have that would fall for C. 36. I'm kind of going a little quick because we're running out of time. I got to leave them for questions, but I might have to run through the next one quickly. So, rank the following substrates from most to least reactive in an SN2 reaction. Again, you already know the whole entire substrates for that. So it's going to, in this case, it should be B. I'm just going to run through with the same concept, so we through really quickly. 37, ranking again from SN1. SN1 is the opposite of SN2, so that's tertiary, secondary, so a lily, tertiary, secondary, primary, methyl. And then so in that case, it should be A, B, C, D, right, or D. So which of the following is the product of an SN1 reaction? So SN1 reaction, so in this case, bromine is going to come off of the leaving group first, so you form this positively charged carbocation. The OH group will attack at that positively charged carbocation, then you get, you would have a yes, a rearrangement, sorry, you have a rearrangement reaction, right? No, you can't. Yes, you can. Yes, you can, I'm sorry. So from primary to secondary, so then, don't forget, for SN1 reactions, you can have carbocation rearrangements, be careful with that. Yeah, almost like that state too. So rearrangement reaction, so now you have secondary program hat on. Yes. And then now you have the OH group attacking at that position. And so um, you will get the OH group here. Or the hydroxide, the OH2 group and deprotonate and everything, so it should be D. You don't want to do resonance structure for this, but then you're just going to go back to this primary carbon cation. You want that secondary carbon cation. SN1 rearrangements are possible, so you want to be careful with SN1 reactions. 39. 39, I know a lot of orbital ones, professors will not do this. This is, you would think if it's a substitution reaction, it would be B, or sorry, it would be A or B. This is one of those things where it's a little bit outside of that. This is a ring expansion reaction. So the ring expansion reactions that you guys learned that originally propane is cycled with butane, and cyclohexane is a stable cyclic compound, right? So in this case, you have a ring expansion to form a cyclopentane instead of a cyclobutane. And so then we would end up getting D as your answer. So I'm going to ask Dr. G about this. So kind of what she thought would happen is something like this, OH2 positive. Then we have a leading group with OH2, so you get this positive charge here. Then you have this carbon, which I would prefer to be in a cyclopentane and cyclobutane with the ring expansion will form a cyclopentane, and you will have a positive charge for that bond to go back. So now you have the bromine attacking at that position, and that's how you get D as your answer. It is a little bit outside of orbital 1, but ACS students, this is something that you might expect on an ACS test. Okay. And 40. So which type of solvent would you use for this compound? So if you look at it, we have a solid line, which means that the SN1 reaction, or sorry, SN2 reaction, because it's going to be dash, solid, I think it should be dash. Should be dash. We only get one compound, so you get dash. So SN1 versus SN2. SN1 is going to be protic solvent and a weak nucleophile. Because if you look at CN functions as a strong nucleophile. It's only a strong nucleophile. So we follow an SN2 reaction. So SN2 is aprotic, strong nucleophile. Like that. Okay. So aprotic, so you want a polar aprotic solvent for this. Again, all your aprotic solvents are your alphabet soup. Alphabet soup. What I mean by that is that you'll sometimes see something like CN, but DMS, just like a bunch of acronyms. DMS, OSCPA, THS, they're just your alphabet. So that's why that's a good way to remember aprotic, the alphabet. And then proton has hydrogen directly attached to a very electronegative atom, directly attached to the electronegative. Usually oxygen, nitrogen. Yes. For tertiary carbon cation, I would have thought you did, but I think Dr. G said that I wouldn't do it until these were complete attachments, so we've already used it, kind of like in our goal, 5 minutes of ring expansion. So something like that, I'm not 100% sure on. I would ask just to make sure about that. Okay. Let's see what we do. So are you passing? Yes, try not to explain the simple word concepts. This should be D, do the naming. You should get that. Parent change should be 1, 2, 3, 4, 5. Like, and you guys can name from there. Number 2, again, naming and all those other things. Make sure that you're doing correctly. 3, 4, 5, 6, 7. And this would be D. So if you're following team E or D. So again, this is where I wanted to kind of take a moment to take a look at it. So here, if we look at this carbon, we have this carbon, carbon. So this carbon is attached to an oxygen and two hydrogens. Oxygen and two hydrogens. This carbon is attached to an oxygen, hydrogen. So you count it over multiply, right? So in this case, this has a higher priority. Let's look at the other carbon. So here we've got carbon, carbon, hydrogen. This is attached to carbon, hydrogen, hydrogen, so this has a higher priority. If you draw a line between the two double bonds, they're on the opposite side, so it's E. So when you do E or D, you want to use it to compare at least three different groups. At least three different. With a dozen. With a dozen. Okay. E, they're going to be on the opposite side. So N is on the opposite side. And D, if you're allies, they're on the same side. So you can kind of get a little, same sign, I guess, something like that. This is not the same thing as cis and trans. Do not say E is trans, do not say D is cis. Because if you have something like this, alright, this four right here. If you use cis or trans, this would be trans, right? Because the two groups are opposite to each other. If you use E or D, on this side this has a higher priority, but on this side fluorine has a higher priority. So they're on the same side, so this is D. So they're trans, but they can also be D. So it's your choice to use one of them. You can use trans and use unit, but make sure that you get the difference between them. Alright. So let's see, rank the following from most stable to least stable. This is Petra is more stable than tri-substituted, better than di-substituted, better than mono-substituted. So when you do this, it should be C. This is Petra. This is dry, this is dye. You're looking at the carbon attached. Number 5, this is one alkyl with a 4 to indicate a product. Okay, we're doing a dot side, so sodium dot side. So NaOH. NaOH, which is a strong base or a strong nucleophile, but in this case, they're going to use it as so this is the product, sorry. This is the product. So you want to be able to do an elimination reaction at the low substitute position. So when you do it, it'll be B. I mean, you have the choice between A and C because D wouldn't really, or D would work also, but when you draw, this is where you can draw a linear projection and do that stereospecific, stereoselective stuff. So you draw the linear projection, make sure that the hydrogen is anti to the fluorine group that's leaving. So in this case, if you draw this one, I'll just draw down just to show you. I'll try to get from this direction. Let's look at my leading group. So it's pointed up, right? And so now we have, okay, looking from left to right, the fluorine will be on this side, hydrogen will be on this side. Okay? So then my back carbon, my phenyl group is down here. This is my methyl group right here. And this is my hydrogen right here. So this allows my hydrogen and my chlorine group to be directly across from each other, which is why I want to use B. If you did A, you would have to rotate it, and that would give you a different product. Okay, so this big drug in projection with the anti-periplanar. Number 6, which is called an elimination reaction. Again, it's a strong non-bulky base. Strong non-bulky base, non-bulky, will give you a Zaitsev product. Zaitsev is more substituted. If it's bulky, you're going to get Hoffman product. Hoffman is going to be less substituted. Okay? This is different. So whether it's bulky or non-bulky, that's the main thing. So identifying it's a strong base and a strong nucleophile, but they want an elimination reaction. So when you eliminate, you're going to want to eliminate towards that middle section. Okay? So when you eliminate towards that middle section, you want to go to C. Because that'll give you a trans. The trans is more stable than the cis. Right? That's the stereo. I want to say selective. This is chapter 8. We don't want to stereoselective, it's stereospecific stuff. 7, which is following shows the mechanism and a concerted reaction. It's going to happen all at once. So the one that happens all at once to correct errors and everything would be A. Here we have to go off of the leading group first, followed by the rest of the reaction. Here we have our proton transfer, which it's just not for the proton transfer from something else. So it'll be A. Alright. I'll try to open that. So number 8, which is the following would be best important reaction. Again, you have a least substituted type. Least substituted, so you want a really bulky base. You want a bulky base that is least substituted. So in that case, it would be every oxide, which you're all familiar with. The hot. Number 9. What is the product of the polymerization reaction? Again, this is a non-bulky strong base. So it's non-bulky strong base. So we're looking for the product of new product. So when you're looking at cyclic compounds, I think you have to be careful of the hydrogens. The hydrogens have to be, I think it was trans, right? Hydrogens have to be trans or be eliminated. So in that case, only possible reduces. Elimination for that should be a hydrogen type. That's the answer. This trans? Trans? Trans for elimination of hydrogen? Okay. So that's going to be trans to the leading group. So in this case, when you eliminate it, the non-bulky, this is this hydrogen right here along the same plane as our chlorine group. So in that case, you can't eliminate the hydrogen, so you have to eliminate the other hydrogen on this side. So your product would be oh sorry, E. You don't change the carbon. Don't change the carbon because you do it exactly. So this is chapter 8. I look on the hydrogen. When hydrogens can't be on, I think hydrogens have to be or start have to be trans. Just check to make sure. Okay. Number 10, which of the following alkyl halides would afford the indicated product upon the reaction with sodium hydroxide? Again, you're using sodium, this is your product, and so you can use one of these, and you're using sodium hydroxide, NaOH. That's a strong base, strong nucleophile. So in this case, it should be C and C. Because again, the hydrogens would be, I think it's actually this. If it's this, it should go. Alright. Take a look at 9 and 10. I'll take a look at it later, and I'll upload a document on the Google site explaining everything. Okay. Alright, number 11. Which of the following alkyl would be the most reactive in an E2 reaction? So in this case, if it's E2 reaction, you want it to be, when you draw the unit projection, I keep drawing the projection after this, so perfect my thing. When you draw the unit projection after this, it'll help make the most stable, because the chlorine will be on the brand to like equatorial position stuff. This is the chair confirmation part of chapter 8. Number 12, what are the steps in the boiling mechanism, or the following steps for this reaction? So we use sulfuric acid, your alcohol is going to attack a hydrogen, you have proton transfer happening, and after that you have a loss of the leading group, right? When you have the loss of the leading group, then you have a rearrangement, and with the rearrangement you do another proton transfer to get the eliminated product at that position. So again, extract the protons, and then you get OH2 plus, loss of the leading group, and OH2 get positive here. To be more stable, just move a proton or a carbon there, methyl transfer. Then you get a positive charge at tertiary position, and then you'll have a hydrogen right over here. Hydrogen, that's going to get extracted by the sulfuric acid. there you should have the, I know the proton was a little funny thing between the two carbons, but, yes. Okay. 14. Addition reactions are favorable at low temperatures because this is a concept question, and then we does these. Alright, number 15, the expected Markov condition. So Markov is more substituted of HI to 2-methylbutene. So 2-methylbutene looks like this. When you use HI, you should get iodine at more substitute position. So when you make this compound, it should be D. Okay. Number 15, what's the major product? So we have a peroxide and a halide with a release substitute side, so we're on B. Right? The reason for that, peroxide will do initiation stuff, so then we get two peroxide radicals. That peroxide radical will react with HBr. So it's going to form HOR plus a bromine radical. Okay? So that bromine radical, when we draw this chair conformation, we're going to attach it to that bromine radical, and now the radical will go on the more stable position with that tertiary position. So when we draw this horrible chair, that's the compound. Okay. You get a radical at that position of bromine there, and to make the radical more happy, it'll extract the proton with a radical proton, and then make it happy. Number 17. So which of the following alkenes would you expect to produce a pyrolysis or bomb hydrogenation of the peroxide? So that means you're using HX as the peroxide. So use something that will produce a pyrolysis center. So you can't produce a pyrolysis with C because it goes on the end. You can't do that. With this one, they have the same exact group on both ends, so that doesn't work. And then for this one, it wouldn't work either because of the end, you have two hydrogens. So looking at these two, you're stuck between either this one or this one would happen. So in this case, it would be B. A would not work because you have two the same groups on that side or two the same groups on that side. 18. Treatment of S-chloral, whatever that is, H0 plus. Acid catalyzed hydration reaction. Acid catalyzed hydration reaction. Okay, so what is expected to produce? That means we're going to put a hydrogen on the most stable position. So we draw our cyclohexane. Fluorines here, we have H3O plus, and that's going to form OH at that position right here. Leave our fluorine alone, so that's going to be 2. Yes, 2. Alright, what's the expected major product? This is an oxymercuration demercuration reaction. Oxymercuration demercuration means that we're going to add on more substituted position. So when we do this, we should get C as our answer because this is our nucleophile. So again, you can replace that with water to make an OH group. You can replace that with whatever nucleophile you want, and that will change the reaction. Okay. Okay. And don't forget, so this hydrogen donates a hydrogen to the least substituted side. That's where the hydrogen comes from. So we're still using ACS, you change that to a deuterium, which is NADBD form. But it's a BD, instead of having hydrogen there, you have a deuterium, you have a D there. Okay? So instead of something like you really quickly, that's the first step, and then use NADBD. Or those CS forms oral too, this can help too. You would get, instead of hydrogen, get deuterium there in that position. Okay? Alright, number 20, what is the second major product of this reaction? This is a hydroboration oxidation reaction. reaction. Okay, so that means it's going to go on the least substituted side, and it's going to donate a OH group at that position. So we look at this, the OH group will go on that side, and so we will get D. Okay. Number 21, oh, kind of shows it too. I mean, but again, pH3 usually donates a hydrogen there. In this case, we use BD3. BD3 will donate a D instead of hydrogen. This is technically like a hydrogenation oxidation reaction. So you're going to add the OH on the least substituted, but that means your hydrogen goes on the more substituted. So in this case, if our hydrogen ends up being deuterium, deuterium goes on the more substituted side. So this would be D. So yeah, this is, if you understand the mechanism behind it, it would make sense how these reactions work. Number 22. What is the major product of this reaction? So we have Br2 with methanol. So when you do this, you should be adding a bromine group followed by a methanol group. This is going to be Br2 with water. Finding Br2 with water, but the water is going to be attached there. So this would be D. This group is on the more substituted side, this gets on the least substituted side, because if you do the reaction behind it, you form the two, you form that ammonium ion. When that ammonium ion comes off, that's the methanol group, or whatever electrolyte you're using, will attack at that position. And that's how you get the growth on the least substituted side after the group on the more substituted side. Again, if you understand the mechanism behind it, it makes sense you have to keep memorizing what's more or less substituted. Alright. 23, which of the following statements is correct when you do the halogenation reaction? So Br2CCl4, this is a solvent. So you're going to add two bromine groups to that position, and you're going to form an enantiomer system, H, which should be B. So when you do that, make sure you do the chirality for it, and then draw the position potential from that. Again, you can do it like I did earlier, position projections. It's a trial error. 24. So treating 2-methyl-2-pentene with 3R2 was a major product, so we draw this out like that. 2-methyl-2-pentene using Br2, but CCl4, whatever it is, you're going to get two bromine groups at that double bond position. So when you name it, it should be a 2,3-dibromine. 25, the reaction with Br2 is cyclohexene. Methylcyclohexene, so 1-methylcyclohexene looks like that. And use Br2 with a solvent, like that. There, that's not a solvent, that's glucophile. ETNH2. That's the same thing as what we did with the alcohol previously on like number 22, like number 22. Then we will also get D. Go to number 22. So if I don't methanol, you have that. You have that glucophile, H2. 26 for reaction rule, MCPDA with H plus H2O plus, that's all should, this should be very similar to a acid catalysis, yeah, right? So you should get 3 and 1 as your answer. That should be E. That's an epoxide. You form an epoxide and you do a chlorination. 27, which is following alkenes would produce the following gene with ozone cleavage by zinc and water methyl. O3 followed by zinc. So what do you use when you have something like that? You have you have an aldehyde, you have an aldehyde and a ketone being formed. So this aldehyde and a ketone group, it's got to be double bond somewhere. It has to be double bond. If it's a carboxylic acid and carbon dioxide, it's going to be a triple bond. So you need a double bond somewhere to figure out a double bond. So it should be B when you cleave it, you should get the right cleaving. That you see the rest of these is not going to be the same structure as that final product. Innovations is use ozone, zinc, and metal. So zinc is used for the study one. 28. What is the expected major product of the following reaction sequence? So we have tryptophan oxide that's going to eliminate our Hoffman product. We get a Hoffman product on the resubstituted side. And with HBr, we're going to add it to the more substituted. So in that case, it should be A, right? Do the reaction, do that. Oh, yeah, yeah. So we have this carbocation reaction is going to happen in this type of reaction, the halogenation reaction. So again, when we do this, we eliminate to get here. Right, when we do the reaction for HBr, we're going to extract the proton. We're going to extract the proton, and then we're going to get a positive charge here. The proton goes here, and then we can get rearrangement reaction right there, and then have bromine come in and attack at that position. So it's helpful to just write out reactions, don't jump to conclusions. That's why I just did this now. But make sure you do that correctly. Okay. Number 29, when you eliminate, you can't eliminate at this position because they're close to each other. So you can't eliminate because they're at the same position to each other. So you have to eliminate either here or here. When you eliminate from either this direction, you cleave it. When you cleave it, you should get E as your cleaving. And again, this should be, you should form a aldehyde and ketone because you form this one. Number 30, which is the following reaction, what would you get for this one? So when you do this, go through each and every single step, you should get 30 as A, right? 31, when you do the naming for this, you can draw out the structure with something like this. You should get D as your structure. D as your structure. All right. 32 is IUPAC naming for this one. When you do IUPAC naming for this one, it should be 32 should be B. 33 running out of time, so I just want to try to figure all of those we can. Should be E. Divalent butane, so you have bromobutane, like that. Using KOH, 100 degrees Celsius, this is called an elimination reaction. What is the expected major product that's treatment and for methyl hydrogen? So when you draw this out, you do this, that's triple bond, and using H2 as the NAR catalyst. For the catalyst, that should create a cis version, so you'll get B. 35, hydrochloric acid, the excess hydrochloric acid. Using excess, you use excess hydrochloric acid, it's going to more substitute side, so you'll form, but then you can't tell which is more substituted because they're both, you can't tell which one is more substituted because they're both secondary carbons, so you'll get two products, this and this. So you will get, when you name it, it should be D. And then which the function cannot reduce your calibration outside. It would be D because they form triple bond there. You can't form a triple bond at that position because you would have 5 bonds of this carbon. Cannot form triple bond there. Okay. Almost done. Number 37, the following oxide is a single product of the hydrogenation oxidation. Hydrogenation oxidation is the resubstituted value, right? Hydrogenation And then, let's see, we have, slightly alkaline listed below, a fraction of ozone part of water that will not produce carbon dioxide. That will not produce carbon dioxide, carbon dioxide. That means you need a terminal. If you form carbon dioxide, you need a terminal alkyne. So the only one that has terminal alkyne that would work would be A. Would not produce, sorry, would not produce it. So you want to see if it's not produce it. Not produce carbon dioxide. So when I produce carbon dioxide, you need terminal alkyne. Alright. Number 39, when you do the reaction for cis, what would you do to get cis 3 octene as your final product? This is going to be your product. And so that should be B. When you do the reactions behind it, it should be B. And then last but not least, number 40, when we do this, we get 2 alcohol groups and there's a deuterium ion there. So that's the deuterium there. And so in this case, you want to go through A to form this product, and then further on we add OSO4 and NaH. That's all I have for you guys. Fill up on your exam. If you have time, please do the survey that we have on the table. So